Peres, visiting from Microsoft Research. So Yuval's a prolific problemist and the author of many textbooks. How many textbooks have you written about anymore? Offhand. You have a new one coming out with Precision right now. And just on a personal anecdote, I got my first experience with research math, talking about research problems with Yuval with my brother who was his student. So I'm really delighted to have him here. And he's going to talk about Laplacian growth and competitive erosion.
So, good afternoon now. Usually this is in the center, so I wonder if those in the back and over there can see it. If not, feel free to move your chairs.
Everybody move up.
So I'm a big believer in Blackboard talks, but I did my duty on that today in the lunch math club, and this topic really goes well with pictures, so it's going to be a slide talk. So it's a real pleasure and honor to be here, and so the first part I'll talk about, will serve the work of many people, but my own work on it is joined with Lionel, Levine, who's now in Cornell. And the second part, focusing on competitive erosion, comes from questions of Jim Propp and his joint work with Shirshendu Ganguly. I'll mention that again later. So there are many kind of ways to start this topic. So one way is to define a rather strange addition operation. So it's a way you take two sets in the lattice and you add them to get a new random set in the lattice. So there's going to be some randomness in the process. And this was defined by Percy Daconis and Bill Fulton. And they had an inkling that this will be good, but they didn't quite know why. And part of this is answering their challenge. So maybe I'll come back to the slide, but it's clearer in a picture what we're doing here. So again, in all these pictures, think there's a fine lattice drawn here, just so fine you don't see it. And then we have two sets. And these sets, in this case, these are the two squares, the blue square and the green square, and you see they overlap here. And in this addition operation, we're going to add two sets, create a new set with some randomness involved. If the two sets are disjoint, then the sum will just be the union. It won't be very interesting. So I took two sets that overlap. How do we add two sets that overlap? Well, think of adding their indicators first. So you'll get one here, and two here. Now think of that, these indicators as counting particles. So initially we have one particle every point here, one particle here, but two particles every point here. Now the excess particles, so every location here has one particle that's want to stay here and one kind of excess particle. And that particle starts walking, a random walk, till it first finds an unoccupied spot. So you go one by one, you choose one particle here, and it starts random walk till it first finds an unoccupied spot, settles there. Then you take another particle, and it walks till it finds an occupied spot, settles there, and so on. And you keep going till every particle has its own spot, and then you stop. So you'll get a set which is somewhat random because the random walks involved. Its total size or area will be like the sum of the areas of the two sets you started with will be equal to that sum. Now there seems to be some ambiguity here because in what order do we choose these particles to move? It turns out that the distribution of the random set I get doesn't depend on these choices. So you can choose any order you like, and you'll get the same distribution on random sets. Okay, so that was in this formal slide, right? To form A plus B, we start with the union, and then we each time define inductively a new set by adding a random walk started at a point xj in the intersection. So that's what I showed you in that picture. And there's this abelian property, the distribution of A plus B does not depend on the ordering of these points in the intersection.
Now the first case of this to be
analyzed is the case when you just keep adding the origin to itself. And this is a process called internal DLA, which was actually proposed in physics earlier. It's related to the more famous and less tractable DLA. So what is this internal diffusion limited aggregation? We start at the origin and we keep adding the origin to itself according to this rule I told you. So what this amounts to is it's equivalent to, you can think of, you insert particles at the origin. The first one just stays at the origin. The next one will walk randomly until it finds an unoccupied spot, and so on. So, so for this, in 92, Lawler, Bramson and Griffeath showed that the limiting shape is a ball. So maybe I'll show you a picture. So this is what you get when you do this a million times. You have each time you start a particle at the origin, the first one will just stay at the origin, the second one will walk somewhere. You know, the nth one will start at the origin and walk till it exits the current set and settle there and so on.
Does this depend on being a square grid, or it makes no difference if it's a triangular or some other kind of grid?
So, right, so for all isotropic grids, it will lead to a disk as a limiting shape. This is a non-trivial fact, first proved by Lawler, Bramson and Griffeath in 92. And for a long time, the question is, you know, what are the fluctuations near the boundary? So if you look closely, you see it's not a perfect disk. And the first proof didn't give any bounds except saying, well, the limit is a disk, so the error or a little O of the radius. Then Lawler proved some power law, and the final answer was found just in the last 5 years by two independent papers, Acela, Godivier, and Jerson, David Jerson, Lionel, Levine, and Scott Sheffield. And they found the error to be logarithmic more precisely. It's log n in 2 dimensions, and it's root log n in higher dimensions when you start with n particles. So,
what did the colors mean in the picture?
So the colors, well, they'll mean more in the next picture, but formally what they mean for every site, we color the color represents the direction that the last particle left the site. So since this is a random process, this coloring is going to be pretty random. But we're going to contrast it with other models where these colorings, but so I didn't talk about the colors. We'll see them more in action in closely related models. Okay, so this is internal DLA. So there are several directions you can go. One is change this random rule to maybe some deterministic rule. Let's see that. Another is change the starting configuration. Instead of adding the origin to itself, maybe start with some other configuration, like what happens with those, adding those two squares. Or if you add two disks. So, so I'll address both of these. So let's see what happens when we change the rule. Instead of being random, we're going to do kind of round robin or rotor dynamics. So let's see this. I'll show you this simulation. So it's very similar, except so we keep adding particles at the origin, but now the movement is not random, rather it's according to these arrows. So each time we add a particle to the origin, then the arrow rotates, so it rotates 90 degrees, and then the particle moves according to the arrow and settles there if it's unoccupied. The next particle, again, will rotate, settle there, rotate, settle there, and now the next particle, when it moves to the right, this space is already occupied, so it keeps going, rotates the arrow and settles there. And so now each time I press the button, the particle is going to do the whole trip until it settles in an occupied spot, rotating the arrows as it goes. And you see that the colors correspond to the directions of the arrows. And you can ask what happens here. And let's run it a little faster. So you see again, it looks like the shape is circular, but this one actually repays freezing the picture. So instead I'll show you, we won't have patience to look at this for a million, but we do have the result after a million.
So this is deterministic?
This is completely deterministic, yet still interesting.
There's some implication that some of us ought to resent, I think.
Surprisingly. So this is, yeah, maybe more interesting than the IPLA. So this is what you get for a million particles. So first thing you see, it's again circular, but actually much more perfect. So I'll tell you, so we have some, we do know with Lionel, we proved this is going to be circular. And we have error bounds that have improved over the years, and now finally just this year we got logarithmic for this one. But the reality seems logarithmic for the IDLA was the truth. There are the logarithmic coefficient. Here, we actually have, I don't have them here, but this has been simulated to 100 million. And if you look at the error, so the in radius minus the out radius, it's never bigger than 2 in practice. So the additive error, it's basically as perfect a disk as it can get, given that it's in the lattice. But our proofs are far behind this kind of perfect roundness. So there's more going on here. Another thing is, what is this pattern? So again, what does the color mean? It means the direction of the arrow, which is the direction of a particle last left the site. So now, because this is a million, the places that you see are actually rather large areas where all the arrows are pointing in the same direction. Like this thing here represents 100 particles that are all going in the same direction. And you see these form a pattern, and those who've studied some complex analysis might recognize it, that it's kind of looks like a conformal map of square root 1 over z. I'll come back to that point. But let me say that the exact circularity is not proved, and the nature of the pattern here is not proved. There's just a lot of empirical evidence. So the theorem we proved like 7 years ago that this shape is asymptotically a ball, but the error bound we got from the top was the power law, and just this year, it's not yet updated in this slide, but just this year, we have logarithmic bounds for the error. Yet, as I said, the truth seems better. But in particular, even the in radius and the out radius, the ratio going to 1 was non-trivial. That was the question that Jim Kropp asked. Okay, now what is this picture? This is you can view it in 2 ways. One is you can start n particles in 2 locations. Maybe I'll show you quickly another simulation that creates this. Same idea. So, okay, that's not what I wanted, sorry. Okay, we'll just focus. So what this picture So what this picture gives you, you can view it as starting with 2 particles, or 2 stacks of particles of size n, one here, and applying the rotor rules to them. Or equivalently, you could think of adding this Diaconus Fulton sum, adding 2 disks, but the rules now are the rotor rules instead of this random rule. It turns out if you do the random rule also starting with 2 disks, you'll get a shape that looks very much like this, but a little fuzz at the boundary. And you can wonder, what domain are we seeing here? The other thing is you see the persistence of these patterns inside. Again, so we do know to describe what is this boundary curve we don't know rigorously, I mean that part is rigorous, these patterns inside are not rigorous, we understood. Now, here's an example of adding two squares using rotor rules. And it turns out that to understand these, it's better to look at a simplified model, which is called the divisible sandpile, which is simpler than both of these, but it ends up giving the same scaling limit. So in the divisible sandpile, we have, instead of particles, we have continuous mass. We start with mass m at the origin, and we keep subdividing it, so each side keeps mass 1 and sends its excess mass uniformly to the neighbor. So initially, we have mass m at the origin, m minus 1 over 4 goes to each neighbor. And we keep going this way, passing to a limit, we get some set where the mass is 1, and outside it the mass will be 0 except for some boundary layer. And if we do this, it's actually not easier to prove that this yields a disk with only an additive error. So this is how this shape looks, so also a perfect disk.
So this is very much like a random walk, except for this stopping when you have mass 1, isn't it?
And there's no randomness in it, right? So we're dividing this as
It's
like
like
the
all possible
expectation.
paths, though, like.
Yeah, so it's like tracking the expectation of a random walk.
So you'd expect something normal if it weren't for this stopping at 1, basically. Wouldn't, if you just took the mass and subdivided and went with no stopping,
That's right.
you'd get a normal distribution. Is that right?
That's right. But here we have this rule that we keep mass 1 at every site, and we only subdivide the excess mass, and this eventually creates this flat disk. Now, the same rule can be used to do a smash sum, a version of the Diaconis-Fulton sum without any randomness, right? So here we add the two indicators, and now we think of them as mass. So, and then we just every site that has mass bigger than 1, divide the excess mass equally among the neighbors, and we keep going, and in the limit we'll get this shape. So the red indicates all the new mass that has settled in, the blue and the green are the old masses. So if you look at these three processes, they're all, there's these differences in the definition, but if you do them, you get kind of the same asymptotic shape.
And does everything have mass 1, or some along the edges only have mass 1/2 or 1/3?
Exactly.
Right
So everything has mass 1, except exactly on the boundary, you have mass intermediate between 0 and 1, but this is only a layer of width 1, so in the scaling limit it disappears. And especially, so all these models seem to yield the same shape, so the challenge was to prove this and to describe what the shape is. And the key to understanding the shape is to look at the right function, which we're calling the odometer function. Odometer in honor of the rotor-rooter model, where the odometer just measures the number of times the arrow rotated. But this function will make sense in all the models, and it will basically measure the amount of mass emitted from a site. So start with the divisible sandpile, which is the simplest model. And U of x is the total mass emitted from a site. This is not net mass. This is the total mass ever emitted. So it's definitely a non-negative function.
Is this something like a Green's function or something? Or not the right analogy, I think?
Well,
We'll see. Okay.
I mean, green functions will have to pop up soon, right? So the discrete Laplacian of this function will have a meaning. So discrete Laplacian is just the average of the values at the neighbor. So this notation means we're summing over y, which is neighbor of x, u of y, and dividing by the degree. So we're in ZD, so this is 1 over 2D. So think of the plane, so d equals 2. So a quarter of the sum of the neighbors minus u of x. And with this function, the total mass emitted from x, this has a meaning. So this is exactly the mass received minus the mass emitted. Because in the divisible sandpile, the mass received at the site x is just, you have to look, the mass will come from the neighbors, and each neighbor sends 1 over 2d of its mass to x. This is the mass received at x, and this is the mass emitted from x. So this difference is the mass received minus the mass emitted. Now, suppose I'm doing Diaconis-Fulton or smash sum of two sets A and B. in this sense. What's going to be the mass received minus the mass emitted? Well, on the intersection, it's going to be -1 because we start at height 2 and we end at height 1. On the symmetric difference, it's going to be 0 because we start and end at height 1. And on the smash sum minus the union, so the kind of the red set, the new point we get, we have this difference is 1. Okay, so because this is the net gain in mass, so it's exactly satisfies this when we're adding the two sets A and B. And now this looks like, like an equation we can solve. We're given the Laplacian of a function, we want to find the function. So, however, it's not the simplest of this kind. It's not a Dirichlet problem because we don't have the boundary. This is known as a free boundary problem. But of the free boundary problems you encounter in PDE, this is the easiest kind. It's known as the obstacle problem for the Laplacian. And there is actually a recipe to solve those in the continuum, and we can follow that recipe. So in order to solve this problem, the trick is first to understand the problem if you didn't have this spec. So everything here is nice and simple except this unknown set A plus B that we're trying to find. So first, suppose you ignore that and try to solve the same problem where you have 1 everywhere outside. So not just in the sum, but everywhere outside. So that's a much easier problem, and you can just write down the solution of that using Green functions. So the inverse of the Laplacian is a convolving with a Green function, and so you can just write down the formal solution, gamma, which will basically, so if I go to this, actually this is for minus gamma, solves exactly this problem, delta U equals this, except that this condition outside is replaced by all x outside the union. That will be minus gamma, and this is just formal solution. Inverting the Laplacian corresponds to convolving with Gaussian, and convolving with the Green function. And also remember that if I want Laplacian, which is a constant, I just take a quadratic. That will give me a constant Laplacian. So that yields this function gamma.
What's the thing that creates uniqueness here? Is it some minimal property? Or?
I'll come to that. So right now we're just getting our bearings. So this gamma is in the right direction. Actually, minus gamma solves the problem on most places, but it kind of misses the point, which is the point we're trying to find what this A plus B is. Okay, so here is a trick going back to Björling, which is to look at the smallest superharmonic majorant of this gamma. And here is and now a miracle happens. The odometer that we're trying to find is exactly S minus gamma. So superharmonic, we're all in the lattice here. We haven't passed through the continuum. So superharmonic here just means this is a function of the lattice, and the value at every point is bigger than the average, or greater or equal than the average at the neighbors. So that's a superharmonic function. And we have this gamma that we wrote out explicitly. We look at functions bigger than that, which are subharmonic, and we try to get the smallest one. And the claim is the difference is that, so here is an attempt to draw that. So this is a version of this gamma corresponding to two dense circles. So we have some function, and the thing to remember is, a quadratic. If you have a quadratic, it will, right? So we know how a quadratic looks, and this function, the Green function, only has logarithmic growth. So when we move far away from the sets A and B, the set will just behave like a quadratic. I mean, the function gamma will just behave like a quadratic. And the quadratic is already, this is inverted quadratic, so it's already minus x squared. It's already superharmonic. So the problem with superharmonicity just occurs inside this compact set here. And now suppose you try to spread, so this is a sheet trying to come down on this, and we're going to spread a superharmonic sheet over this function. So most places it will fit tightly, but there will be a compact set where the sheet will be above gamma, and that's what we care about. And then when we subtract, we'll get a compactly supported function. And this compactly supported function, I claim, is exactly the odometer function we're after.
Shouldn't it be a concave hollow or something like that?
No, but it's not far. But it's not exactly, it's exactly the superharmonic majoring. And in fact, even though it's a colloquium, this is something that's, simple enough that I can show you the reason, and it'll fit in one slide. So let m of x denote the amount of mass present at x in the final state. Okay. Then, claim the Laplacian of u. So remember, that's the mass received minus the mass emitted. It's exactly m minus indicator a minus indicator b. So m is this function m of x. This is the mass at the end. This is the mass when we start. This is an exact identity. And the mass at the end is always at most 1. It's 1 on the set that we want. It's near 0 and 1 in the boundary and 0 outside. So we have this inequality. And now, remember, gamma was written so that its Laplacian is exactly 1a plus 1b minus 1a. This is in the whole plane. There are no complications here, no mysterious a plus b. So this is an equation we could formally solve just using Green function. So gamma was designed to satisfy this. Now, when you add this, you get that u plus gamma has a negative discrete Laplacian, which by definition just means that this is a superharmonic function. So u plus gamma is superharmonic, but what was s? S was the smallest superharmonic function above gamma. So u plus gamma is at least s. So that gives us one inequality. Remember, what are we trying to prove? We're trying to prove that u equals s minus gamma. So this says u is at least s minus gamma. Now, we want to prove another direction, and we have very little space left on this page, but nevertheless, this is it. So for the reverse inequality, let's look at any, remember, S is the smallest superharmonic major. Let's look at S minus gamma minus U. So this is a function which is superharmonic on A plus B. Why? Because if you take its Laplacian, the Laplacian of gamma plus u, if you look here, on a plus b, the Laplacian of u equals. So this inequality is an equality on a plus b. Because that's where the mass is 1. So on a plus b, Laplacian of u exactly balances the Laplacian of gamma. So on a plus b, gamma plus u has a 0 Laplacian. So this whole thing is superharmonic on a plus b. So it's superharmonic on a plus b. And outside a plus b, what we care about is really on the boundary, but on the outer boundary of a plus b, this is non-negative because, why is it non-negative? S is always above gamma, and outside a plus b, u is 0. Because, no mass comes out of points outside a plus b. So outside a plus b, u is 0, and s is always bigger than gamma. This function is a function that's superharmonic, and it's non-negative on the outside of a plus b. So just the minimum principle tells you that it has to be non-negative inside also. And saying that this is non-negative is exactly saying that u is below s minus gamma, which was the other inequality. Okay? So it's kind of a miracle that the function that we're trying to determine has this recipe. And once this miracle happens, we're well on the way to doing scaling limits because it's hard to understand, actually, to make sense of the dynamics of these particles in the continuum. It's possible, but hard to analyze, related to so-called the Stefan problem in PDE. But when we phrase things like this, like if we this identity, S minus gamma is an object which has a meaning in the continuum. We can find, we can use this recipe to calculate gamma in the continuum. We just, x squared stays x squared. This sum will become an integral. We know the Green function. in the continuum, and so everything is set to pass through the scaling limit, and indeed, that's what works. So in the continuum, we define gamma by this recipe. We define S as the smallest continuous superharmonic above gamma. That was the Buehling recipe. And then the final domain we want is A together with B together with the set where S is bigger than gamma. That's the support of this continuous odometer. So we don't have a direct meaning of odometer in the continuum, but we just define it to be S minus gamma in the continuum. And then we can just prove that there is a limit, and we can say what it is. So, for instance, this is the domain when you have two overlapping disks. And it turns out these kind of domains have been well studied. They're known as quadrature domains for any complex analysis here. So, so remember a harmonic function, its value at the point is the integral over a disk of unit area around the point. And you know, if you take 2 points, you say I want a domain where if I sum a harmonic function over these 2 points, I'll get the integral over the domain, and the domain will look like this. Like the picture is much better than what I'll draw on the board. Now, to get the domain specified uniquely, you have to be a little more precise. So instead of just saying, you know, about harmonic functions, talk about superharmonic functions. So a quadrature domain. So, you know, if you have one harmonic function, its value at the center is, of course, bigger than the integral over a disk. I'm taking a disk of unit area. And similarly, for this domain, if you take any superharmonic function and add it at these 2 points, it's bigger than the integral over this domain. And that already uniquely specifies the domain up to 0 measure. And that's these quadrature domains that have been studied in complex analysis since the 70s, and in particular, when you have a quadrature domain determined by finding too many points, boundary is an algebraic curve. So we can say what happens for these. And all the models that discussed have these scaling limits. So this is a formal statement of the result I just told you, and you can put different masses at different points. All the theory, you don't have to have equal masses. All the theory extends to that case. And you know, there are steps of the proof. Each step is a little harder technically than what I described. And one technical point that took us a while is, in order to make these proofs go through, we really have to make sure that that before we know what is the solution of this pre-boundary problem, that the boundary of the domain we get must have 0 area. You know, there are Jordan curves in the plane that have positive area, and these are kind of the nemesis in this problem. Luckily, there are, you know, techniques of Caffarelli to handle boundaries and free boundary problems, and we just have to use a few of his techniques to handle this case. I'm going to skip the technicalities here, and then there are more techniques. So I talked about the divisible sandpile, and all this extends to the other models, the IDLA and the rotor models, and there are some, so you have to do some smoothing to handle, because the things that are exact identities for the divisible sandpile have some small errors in the other model. You have to handle the errors, but that's something, you know, we don't do in Colloquium. So, but there is a paper on this published already a few years ago in Geodesic, if you want to see more details.
I didn't quite understand what a quadrature domain is.
Okay, sorry. So a quadrature domain, I won't give the most general definition, but given, let me go back to, sorry. Okay, maybe I have it here. Okay, so a quadrature domain is just, okay, here's one thing that the domains, quadrature domains are. You have a bunch of points, x1 to xk, and weights lambda 1 to lambda k. A quadrature domain satisfies this identity for all harmonic functions and an inequality. So the left-hand side should be less than the right-hand side if h is superharmonic. So again, if you just have a single point with weight 1, then the quadrature domain corresponding to that is the disk of area 1 around the point. because we know that the value of superharmonic function at the center is bigger than the integral over the domain. If I have, and the picture that you saw there, this picture corresponds to a quadrature domain, represents a quadrature domain with 2 points and equal weights at the 2 points. And so this domain has a property. If you take any superharmonic function and integrate it over this domain, this is less or equal than the sum of the superharmonic function at these 2 points, at these 2 centers. And this is the only domain with that property. So that is, uniquely determines the domain. And you can see why we're going to get this domain when we do our process, because if you take a superharmonic function, think of it as a lattice now, and just look how it's evolving along our process. So say the divisible sandpile. Each step of the divisible sandpile, what are we doing? We're taking some math and dividing it among the neighbors. So if we have a superharmonic function on the lattice, so the value at the center is bigger than the average of the neighbors, this function will be decreasing in every step. So it must be also smaller in the limit than what it was to begin with. So it's easy to check that what we will get here is a superharmonic. Is the quadrature domain, and then those domains are known to be unique and are well understood. Okay. So I'm going to skip the approximation steps. Right, so this is the quadrature identity we have for this domain. This is for harmonic functions we have an equality. So for rotor, I told you we have, so this tracks the maximum difference of the out radius and the in radius of the set. And you see this is really small. So one conjecture is that this should be bounded. Here's one question. So when you look at the occupied region at any finite stage, I'm talking now about the, say, the rotor dynamics, then it looks simply connected, but we can't prove that. So there seem to be no holes.
Can you prove that it's not if the arrow twists too much?
What do you mean by too much?
No. More?
So we had a twist, 90
Because you
degrees.
had a twist 90 degrees. What if you had a twist 180 degrees? Would it be simply connected?
It still looks simply connected, yeah. So you have to do some, so the general thing, right, so I told you about I drew it in 2 dimensions, but this sets make sense in d dimensions, and you just need some ordering of the neighbors of the origin, and for all orderings, this looks to be simply connected. This is some variance of the set. For instance, here there's a one-sided mirror that, so particles coming from the top can go to the bottom, but particles coming from the bottom can't go to the top. Again, there seems to be a scaling limit for this, which has some analytic formula. We can't prove it. Here is what I told you before. This pattern looks like the picture of √1/z. So to see that, suppose you apply the inverse map, 1/z squared to this picture. Right, so that's inversion and squaring. So what's going to happen? The outside of this is going to go to this white disk here. And the inside will go to the complement of this. So the fact that I cut it off in this square is just for visualization. This really continues to the whole plane. But the point is that the pattern that you see here becomes like a lattice pattern once you apply this map. But we can't prove anything about this picture. So this lattice pattern appears, but we can't prove it.
Does that depend on it being a square lattice? If you did a triangular lattice, would you get something different, or?
No, we still get the same pattern, square picture. So the square, it's more related to this map. Okay, so there's lots of other models. So this is, a close relative, which is the sandpile model, which, sounds almost the same. So you take when. So this is the dynamics of the sandpile model. It started with 0 height. So what does this, how does this differ? We also have particles at the origin, but now a site topples only if it has 4 or more particles. If it has, then it sends 1 particle to each neighbor. So this is, I talked before about the divisible sandpile. This is the undivisible, the original abelian sandpile, where, so again, a site, you add particles at the origin. When the site gets 4, it sends one particle to each neighbor. And that's true for every site. So it looks like pretty similar to the models we discussed before. However, the scaling limit doesn't appear to be a disk. And for a long time, we couldn't prove that it's a disk. And it looked like we couldn't prove that there is a scaling limit at all. And it looked like the PDE approach was doomed for this, because when you do this model on different lattices, you get different shapes. So you see the flat part on the top. So there was a remarkable paper a few years ago in 2013 by Charlie Smart and Wes Pegden, where they showed the existence. They showed the existence of a scaling limit by a PDE approach, but the scaling limit depended on which lattice. So it was also a free boundary problem, but a much more complicated free boundary problem, where the PDE that you got depended on which lattice you worked on. And there's further work of Pegden and Lionel, Levine, Wes Pegden, and Charlie Smart, getting some information on the scaling limit, but it's still not far from fully understood. And okay, so maybe I'll finish this and tell you about the most recent model in this class we've analyzed. So what you see here is a close relative of the internal DLA. This is known as competitive erosion. So what is the process here? We have a blue source and a red source on the top and the bottom, and they alternate. So we start with a random configuration with some fixed proportion of blues. Say in this picture, 1/3 of the locations are blue, 1/3 are red, and it's just divided randomly between blue and red. Now in each round, a single blue particle walks randomly till it hits the red set, and then it converts a red point to blue. And then to balance that, a single red particle moves from the red source and moves until it hits the blue set and converts a red to blue. They would have asked you, well, what do you think will happen in the long term? But you kind of see. So there's a clear interface developing, and you can kind of see what this interface is. It's a circular arc, orthogonal to the endpoints, otherwise known as a hyperbolic geodesic. This model was proposed by Jim Propp, who conjectured that not only this, but in general, you should do, if you do this in any domain, this process will be conformally invariant. So in other domains, you'll get different hyperbolic geodesic corresponding to that domain. And we have, so the last part, let me tell you what we have on that. So we do know this under some assumptions. So again, this is a description of the processing. So, we have a red source and a blue source. A particle starts from the blue source and moves. We started here. It moved, it conquered the red location and converted it. And then a particle starts from the red source and it reaches the blue location and converts it. That's one round of this dynamics. So we started in this configuration, we ended in this configuration. Note that there is preservation of mass here. The total number of blues stays the same, because we convert one and then we convert one the other way. Okay, so this is contrasted with IDLA, which I told you about before. And I'm just going
Can I just ask about the erosion model you were showing?
Yes.
The blue and red sources were on the boundary.
Yes.
But you could make a source in the interior, couldn't
Yes,
you?
you
But then the hyperbolic units wouldn't make sense as the boundary. Well, It might make sense, but it wouldn't be the right answer.
Right. So that can be analyzed as well, but I'm focusing on the boundary case here. So this is the model here. There's a lot more to understand. So we only understood the case where the initial sources, we only have understood in the paper rigorously the case where the boundary, the initial sources are on the boundary. In fact, they're little blobs which are shrinking. So we don't actually start with a point, we start with a little blob. And so this is the picture we got there. And in a general domain, so this is some general domain, we'll also get a hyperbolic geodesic. So just take, okay, we can prove things only for simply connected domains with an analytic boundary. But theory should be much more general, but this is how far we've gotten. So we assume that the boundary forms an analytic curve. Now one thing to keep in mind is that a conformal map doesn't preserve areas. So if I have, suppose I want to understand this domain and I have some proportion, say 40% blues, then I can't just find a geodesic here that corresponds to 40% blue, because when I map, it won't preserve the area. So you really have to look at this whole family of geodesics. When you map them here, you get the whole family of geodesics, and one of them will correspond to the right proportion of blues, which is the initial proportion, and that's the one you want. So the real thing which we can prove involves starting with little blobs like this and eventually shrinking them to a point. So you start the point uniformly here, and then a red particle uniformly there. So one can write all these geodesics analytically. I will spare you this detail and just tell you what is the main difficulty, and then I kind of have to finish. So why is it natural to get the hyperbolic geodesic here? I mean, when you look at this picture and okay, this is supposed to be this, if you have 1/3, 2/3, someone might naively guess, not anyone here, but someone else much more naive, might guess that the boundary is a straight line, but it's not. So how could we guess that it is if there is an interface, there's a very compelling argument that says it should be a hyperbolic geodesic. Go ahead.
I don't know.
Point to Chris, because it's a harmonic measure argument. If we have any interface here, like this, and the particles from the bottom, the blue particles are pushing the interface up, and the red particles are pushing the interface down. So any stable interface, these two pressures have to balance, which formally means the harmonic measure from the bottom should balance the harmonic measure from the top.
Oh, I like that.
And now, without knowing any complex analysis, we know that if the mass was half-half, then this would be just the diameter by symmetry. And because harmonic measure is conformally invariant, you know that if you apply any Möbius transformation to the diameter, you're going to get a curve where the harmonic measure from the bottom and the top will coincide. And that's exactly the family of hyperbolic geodesics. So images of conformal maps of the disk to itself. If you apply this straight line, you'll get these. So that's why it's easy to guess that this should be the right interface, and indeed to prove if you know that the final shape is an interface. The technical difficulty in the model is that, so this is this picture, if the limiting interface, if there is one, has to have this harmonic measures from both sides the same, and that is this hyperbolic geodesic. But the problem is that we start, remember, in a jumble, blue and red everywhere at random. There's no interface really apparent. So that approach only works kind of when you know there's an interface. So you have to work with suitable potential function. So you start in this. How are you going to show that things are getting better? So the basic idea is to look at the look at the total height of the blue particles. The blue particles should be going down. So the total height of the blue particles should be decreasing. But it's not exactly height, right? So the right thing to use is a bipolar green function, and that will give you the right improving Lyapunov function. So dipole Green function. And there are interesting details here which won't fit in a colloquium. So just want to quickly tell you something about what goes on. So the trick is to look at a set of good configurations. So mega epsilon are configurations where there are fewer than epsilon n squared vertices in the wrong color. And then we want to show that we basically enter this set and tend to stay there for a long time. So the key is to look at the right function, a function where function W that will be bounded but will be improving in every step. So its expectation will improve in each step. And this function, it's going to be, I'm going to skip ahead a little and just get to what this function is. So this is a construction of a bipolar Green function. So it counts, so Gn of x, you start at x and you count what's the total time I'll spend in the blue source compared to the total time I'll spend in the red source. If I would integrate just this thing, it will be infinite. If I integrate just this thing, it's infinite. But the difference goes down, and it's integrable, so it makes sense. And the value of the integral depends on the starting point, and it's a version of a Green function in the sense that its Laplacian will give me +1 at this one source, -1 at the other source, and 0 outside the sources. And then the right function to look at is just adding this dipole Green function over all the blue particles, and that turns out to improve in every step. So I'm out of time to explain that, but let me say that approach only handles, so there are lots of details I'm going to skip, but I'll say this approach only handles the, again, sorry about this, but this approach only handles showing that most particles are on the right side. And then you need a separate kind of cleanup argument to show that there's no dust on the wrong side. So and that took us a while longer to prove. Finally, let's see. If you are interested in more details, I recommend we have a couple of papers on this. And one, which is much easier, is joined with Lionel, Levine, and Jim Croft. But even that is non-trivial. So you do the same model in a cylinder, so the one source is the bottom side and the other source is the top. And so a particle just starts at a uniform chord here. A blue particle moves, conquers the red side, and then you have a red particle here. So here the interface is just going to be a straight line, and the Lyapunov function is just the total height of the blue particles. So similar ideas to what it's trying before work, but it's technically much easier. And this work was actually a guide in the more complicated analysis that I flashed by. So let me end with just saying some models so one can start with the sources in the center, and I think the techniques would extend to that case. But the case that's completely mysterious for us is, and very interesting, when both the red and blue source are in the same location. So you alternate red and blue particles. Particle starts and walks till it either reaches an unoccupied site and stays there, or reaches the other color and converts it. So in this case, most particles will just convert other particles. So this will be a growth model that will be quite slow growth. And there seems to be some kind of spiraling out, but we don't understand it at all. That's one challenge. Another challenge that looks more modest, but I don't know what's going on, is 3 colors. Right? So you have 3 sources. This is the case, a symmetric case, where you have the same size, so it's clear what the shape is going to be, and it is that. In simulations, we haven't proved anything about 3 colors. But if you start with 1/10 green, 4/10 blue, and 5/10 red, what's going to happen then? How are the domains going to look? I have no idea. I have no proof of convergence. And let me just say that you have to be a little bit careful here, because when you can't just go through the domains in sequence because then one color would take over. What you do is you start the green particle and see what happens. Did it swallow a blue or a red? If it swallowed a blue, then the next particle to move will be a blue, and so on. So each time the next particle to move was the one who just lost a particle. Mm-hmm. And that way you keep the preservation of mass, so the problem makes sense, just we have no solution. Is there some conformal invariance with 3 colors? I don't know.
Did you simulate?
We did simulate, but not enough to make conclusive statements. Here are some papers on this second half of the talk, and thank you for your attention.
Thank you.
I have a curious question.
Yes.
You work for Microsoft.
Yes.
What complicated advantage does you said people Microsoft?
You obviously you should have come at 1 o'clock for the math club, where I talked about prediction with expert advice. Another answer to your question is, I work at Microsoft Research. So I do a lot of research of different kinds. Some fraction of it is relevant to Microsoft, and some is not. Any other questions?
Well, I'm just wondering, what you're doing here was depending on like a lattice or a grid or something. I wonder if there's a continuous version of this that might make sense in a sphere or a surface or a manifold where you have maybe things moving by Brownian motion or disks moving, spheres moving by Brownian motion.
Yes, you could.
You haven't written that paper yet.
No.
Okay. We'll work on it.
Well, it's funny because even if you put a Riemannian metric there to make the distribution of the particles anisotropic, the harmonic functions will still be the same. So it's really not obvious all around.
Well, the picture with the 3 colors is reminding me instantly of some problems involving eigenvalues on spheres. Because that picture happened to look like a certain eigenvalue picture on a sphere. But on a sphere, there's not really a good lattice because it's hard to, there's not. But you can make a continuous version like the disks originating and moving by Brownian motion to the head, and then you might expect an analogous theory where there's not a really discrete theory that's easy to write down.
Right, but as long as we believe in conformal invariance, we can do the stereographic projection and analyze it on a lattice there.
So currently, is there like some big holy grail conjecture? I mean, what's the thing people really, really want to know? Someone's going to win a Fields Medal on this. What's the problem they have to solve?
So the one thing I carefully avoided is discussion of external DLA, where so that's the explanation, where particles, instead of moving from the inside, they move from the outside and stick to the current shape. And while internal DLA is a smoothing operation, external DLA is an unsmoothing operation. You have some fingering, and understanding the extent and the fractality of that, that's something we studiously avoided here. But
that's where the money is.
That's where the fame is, yes.
Well, thanks again.